what you're going to do is you're going to look at this chart. So let me explain a little bit how it works and what the notation means. So notice that the chart has a function over here. So basically, if someone took this function and plugged it into the calculator, and then let's say they plugged in negative 1,000 for x, this is what they got for y. When they plugged in negative 100 for x, this is what they got for y. Okay? So I used really small numbers. Negative 1,000 is really small. Okay? I used kind of ordinary numbers to 0, and then I started plugging in bigger numbers and a really large number, like positive 1,000. Because what I'm trying to figure out is there a horizontal asymptote or not? So remember we said the function can do a bunch of crazy stuff in the middle, but the horizontal asymptote would tell you what it does kind of at the end. So what I'm looking for is does this kind of mellow out at one number and keep just like kind of following that number or not? Is it just like keep climbing up forever, keep going down forever? What's happening? So this here, scared of the notation. It says the limit as x goes to negative infinity. All that means is as you start plugging in really small numbers for x, what happens to the value of your function right here? Okay? So to make this point, I'm actually going to look at a different one. Let's look at the middle section of your handout. So if you guys can see, I know they're not numbered, but they're kind of like there are some darker, bolder lines that divide the sections into like 5 functions at a time. So there's like the top 5, and then the middle 5, and then the bottom 5. Okay? So in the middle 5, let's say we look at the first one there. So this one. And look at what's happening. So remember, you guys have the chart all together, but this was like when x was negative 1,000. This was like when x was positive 1,000. And these were numbers in between there, okay? So let's just say I started at 0, and I got negative 15. Is that right? Yeah. Okay, so I plug in 0, I get negative 15. Let's say I just want to look at what happens when x starts getting bigger. So graphically, I'm thinking, okay, fine, you plugged in 0, you got negative 15. But what about when you look way down here on the x-axis? Does the function keep climbing? Does it keep falling? Or does it start looking like a straight horizontal line that's at some number, like 5 or 10 or something like that? So that's what these numbers are allowing me to do. 1,000 is pretty far down there for me to look at. Okay? So I'm trying to see, does it seem like it's forever climbing, or does it seem like it's kind of mellowing out at one number? So it goes from negative 15 all the way up to 10.5. Then from 10.5 back down to 2.5. Then from 2.5, it goes to 2.05. And from 2.05, it goes to 2.005. So does this seem like it's still drastically climbing, drastically falling, or kind of mellowing out at one number? Yeah, and what number does it seem to be approaching? 2. So that's what I'm going to put right here. Okay? Then look at it from the other perspective. What if you started at 0 and you went this way and you wanted to see what's happening way out there on the graph? That's what these numbers are here for you. If I plug in negative x values all the way out to negative 1,000, look at what's happening. So it went from negative 15 to negative 2.25 to 1.45, then to 1.94, then to 1.99. So again, does it seem like it's increasing, decreasing, or mellowing out at one number? One number. And what number does it seem to be mellowing out at? 2 again. Okay. Make sense? So I plugged in all the numbers for you guys. I didn't do that for my class last year. I'm sure they hated me because it was really annoying to plug all this into the calculator and try and fill in all these numbers. I just want you guys to really look for patterns. Okay? So going back to the very first one on the worksheet, okay, we'll do one more together, and then I'm going to let you guys work in your groups and look for the patterns you think that you see. Once you've filled in all these numbers, we'll look for patterns of, like, why did they split the functions up this way? Like, what seems to be happening? But we can't make those decisions till we've looked at this. So if we look at the very first one, again, positive numbers. When x was 0, we got 0. Then we plugged in 1, it gets 5. Plug in 10, 50, 100, 500, 1,000, 5,000. Does it seem to be increasing drastically, decreasing drastically, or kind of mellowing out at one number? Just increasing forever. So what I'm going to do is just say it doesn't hit any number. In other words, because it's increasing, I'm going to say it goes to positive infinity, because I don't have a number to label it with. It just keeps climbing. Okay? And then looking at it in this way, goes from 0 to -5 to -50 to -500 to -5,000. What's happening there? Same thing, except for it's going down, negative. So we still say infinity, but to tell people up or down, we do label infinities with negatives and positives sometimes. So that's positive infinity to tell them it's like climbing up forever. And then this one would be labeled as negative infinity to tell them it's not stopping at one number. It is going forever, but it's going downward in that direction. Okay? So do you guys get what you're going to do? So you're going to fill out the remaining problems in this chart. This chart is part of your assignment sheet, so it will get stamped and on there. So you'll get credit for what you're doing in class if you are like, why should I do this? One, it's going to help us learn, but two, you get points for it too, okay? All right, so fill out the chart, and then we'll try to draw some conclusions. So use the people sitting at the group that you're in to fill it out and make sure you're in agreement. I know the copy kind of sucks. I'm sorry. It's because I have to scan it first, and that's just how it looks, but try to deal with that. And then take some time to figure out. Okay, first section. Okay. Okay, so first section of functions. Okay. Second row. Who can give me limit on the left side and limit on the right side? James. Good. Okay, so first question I got asked. Is it okay that both of them are negative infinity? And the answer is yes. Could you draw a function on the graph where both the ends just end up going downward? Yes. Okay? So that's okay. All right, next one. Okay, third function in this group. Who can give me limit on the left side, limit on the right side? Alexis? Good. Okay. So again, in both of these, it went from 3 to 30. So I was seeing people write down like 300. 300 might be your next prediction, but then 3,000 might be your next one. Because it's not staying at one number as you would go further and predict it, that's how you know you're headed towards the infinities or the negative infinities. Okay, what about the last one in this top section? Who can give me left end and right end behavior? Steven? Good. All right, so all of these functions, this is one group of functions. They were grouped together for a reason. We'll try to establish that reason in a little bit. But notice that all of these have end behavior. That's what we call what they behave at the end, okay? That's similar. Not similar in where like some of them have two negatives. You could have two positives. Some of them have a negative over there and a positive over there, or vice versa. So there's no pattern there, but the pattern is none of these evened out to a number, okay? And there is a reason why. There's something about the way these are structured that they don't even out to a number at the end. And we're going to establish that a little bit later. So in this first group, it was all infinities and negative infinities, and there's something about the way they're built. And that's going to be key for us, because if we can figure out how these are built that establishes that they aren't going to level out anywhere, then we'll know that these are the ones that will not have any horizontal asymptote because they're not going to level out to one number. Instead, they're going to have that oblique asymptote, so they shoot up or shoot down in some direction. Okay? So why that happens, we'll figure out in a minute. Okay, second section. So we did the first one together, end behavior of 2 and 2. So the second function in this section, can anybody tell me what they think for left end and right end behavior? Alexis? Good, so 0.2. So here you can see 0, 0.19, 2, 0.194, 0.199. So if I had to predict the next one, I think it's going to go like 0.1999, and eventually I'm just going to have this whole like 0.199999 with more nines, which basically is going to make it look like 0.2, okay? So that's how I see that. And then here you can see 0.3, 0.206, 0.2006. I would predict like 0.20006. Those kinds of things would eventually just lead it to look like 0.2, okay? All right, what about the third function right here? Yeah? Good. So negative 0.3 for each side. Again, because if you tried to continue the pattern, you just saw more 0.3333, okay? And actually in this one, you're totally right. We're just observing. So, but to make it easier for you to find a pattern, it's actually a 0.333333. As you can see, you can kind of see them building there, and that kind of makes sense. I'm telling you that now, so when we try to look for it over here, it makes sense as to why it is. Okay. All right, and what about the last one in this middle section? Yeah, Holly? Okay, so we got 4 and 4. Okay. So the functions in this middle section, do you think they're going to have horizontal asymptotes or oblique asymptotes? Horizontal ones, because at the end, they're going to kind of level out to one straight number instead of shooting up or shooting down like the infinities, okay? Do they level out at one specific number? No. How is this number determined? Again, there is something about these functions that tells me, A, it is going to level out at one specific number, and B, what that number is. So there's actually something about this function that I can tell this is going to be 2. And there's something about this function that I can tell it's going to be 0.2. Okay? We're going to look for that again in a little bit. Okay? So again, we're kind of determining there's some different categories here. All right, so last section of the handout. Okay? First function in that row. What do we see for left end and right end behavior? What do you guys think? Yeah, zeros, okay? So for some people with the negatives, that's a little confusing, but can you come up to 0 from a negative? Like on a number line, could you come from the negative side and get closer and closer to 0? Okay, you could. So that's what's happening here. Negative 1.6, negative 0.3, negative 0.03, and then I would predict like a negative 0.003, and more of that happening would eventually just lead it to look like a 0, okay? And then same thing on this end. All right, what about the second function? Yeah, Alexis? Good. Again, 0, 0. So here you see 0.1, and then it's kind of like a 0.02 if you round it, a 0.002, okay? If I had to guess again, 0.002, okay? All those zeros are eventually going to lead it to kind of look like 0, and same thing happening on that end. What about the third function in this? That almost came out wrong, right? The third function in this row. Ideas? Yeah, 0, 0. So there is a pattern forming here. So you can see 0.5, 0.06 or 0.07, 0.007, 0.00007. Those are going to end up eventually looking like 0, and same thing on this side. So what do we think for the last function here? 0, 0. Okay. So there is something. So does this function have a horizontal asymptote or an oblique asymptote? Horizontal. It levels out at one number, okay? So we saw a category that has oblique asymptote instead of horizontal, and we saw 2 categories of functions that have horizontal asymptotes. The last category, they leveled out at some number. How that number is determined, we don't know yet, okay? This category, what did they all level out at? 0. So there is something about the way these functions are written that would tell me not only do they have a horizontal asymptote, but it is specifically at 0 and not at any other number, okay? So what I want you guys to do now is take a couple minutes, and I want you to see if you can determine, like, why are these functions different than the ones that were in the group before, different than the ones that are in the group before. So instead of looking at the numbers now that we filled in, I want you to look at how the functions are built or composed and see if you can find any pattern of what do these have in common and what makes them different, than these other ones. So each group of functions has something about them that's similar, and each group is different from the other groups in that way, okay? So just with your group, take a while, just observe. Some things are going to be totally random that you're going to bring up that I didn't think of, because you're just trying to figure out if there's a pattern there. Does that make sense? So just a couple minutes, okay, whatever ideas your group can come up with, and then we're going to ask every group to give us an observation that they found. So come up with something. What does each category of functions have in common amongst the functions, and how is that category different from the other categories on the paper, okay? So those 3 sections. All right, so I'm going to give you guys literally 2 minutes. Hold true. Yes. Is that different from the other groups of functions? Yes. Okay, Hannah. Okay, good. In the second group of functions, Alex, turn around so you can hear this. It's important. Okay, in the second group of functions, Hannah's pointing out that numerator and denominator have the same power on the highest power of x. Does that make sense? So x to the first, x to the first. X squared, x squared, x squared, x squared, x cubed, x cubed. Sure. Okay. All right, Molly. Good. And in the last one, the denominator has a greater degree. Okay, so when you guys are saying power, the word degree translates to the highest power in some string or polynomial function that has lots of different x powers in it. Okay, so degree is the word we're going to use to describe that highest exponent. And what you guys have identified is exactly right. So in the bottom section, degree in the denominator was bigger. In the middle section, they had the same degree in numerator and denominator. And in the top section, okay, the numerator had higher degree. So I'm going to write what James wrote on his paper because it kind of sums it up, okay, that basically if you simplify these, okay, kind of ignoring all the extra plus and minus stuff, they will basically end up with some power of x in the numerator but not any power of x in the denominator. So this is why they don't settle down at a number. If you keep plugging stuff in here, is it going to keep growing? Yeah, okay? Whether it goes up or down is going to depend on some of the other things more specific to the power, but basically this is going to grow and this isn't going to keep up with it, so that's why it doesn't level out at any number. Okay? Then in the second section, he wrote this. They have the same power, so basically what's going to happen every time is you have this same power of x, okay? Which basically, what does this simplify to be? 1. But did all these end up at 1? No. Why? Any idea why? So they all had the same power of x, but what did they have that might be different, that might have dictated what these numbers are? Coefficients, right? So if I had a 2 here and a 3 here, what would that simplify to be? 2/3, right? So take a look at this. Instead of just seeing it as a first power of x over first power of x, think about if you had 12x over 6x, what does that simplify to be? Okay? And if you had 1x squared over 5x squared, what does that simplify to be? 1/5, and if you divide that out, 0.2. Okay? If 9x squared, what would that simplify to be? 1/3 negative, because our numerator is negative, negative 1/3. Okay? And over here, 8x cubed over 2x cubed, that would simplify to be 4. So we know that when the degrees are the same, they're going to even out at a number, not a consistent number for every different type of function, totally going to depend on the coefficients of those matching degree x's. Okay? Last section, okay, he wrote this, basically kind of the opposite or the inverse of the first one. The powers might work out a little differently, but basically, because you have a higher degree in the denominator, if you could keep simplifying stuff, you're going to end up with powers of x down here, but not any up here, right? Which means if people keep plugging in bigger and bigger and bigger numbers down here, you're going to have 1 over a bigger, bigger, bigger number. What happens if you take 1 and you keep dividing it by something that's getting larger and larger? It gets smaller and smaller and smaller and smaller and basically approaches 0, which is why those ones all even out at the same number. Totally doesn't even matter the coefficients because this behavior kind of dictates what's going to happen. All right? So we basically want to summarize this and put this into the notes that I gave you yesterday where you had places to write how to find a vertical asymptote, how to find an x-intercept that we reviewed right at the beginning. So we want to go back to that. That's not that part of it. This part of it. Okay. So we already talked about vertical asymptotes, holes, and x-intercepts yesterday and determined how that would work. And now you guys have just determined how we're going to figure out if it has horizontal asymptotes or oblique asymptotes and how we're going to know which horizontal asymptote it is, right? Sometimes it's going to be at 0, and sometimes it's going to be at a different number depending on if the degrees match and we take those coefficients of them, okay? So for the horizontal asymptotes, okay, there's going to be 3 cases. You're going to want to make sure that you have that organized. So this is the paper that we had yesterday. Okay. So the 3 cases were, and I'm just going to write in parentheses that everything I'm writing up here is about the degrees. Now remember, the word degree means the highest power on x in each part of it. So the first case that was in our chart was when the numerator was bigger than the denominator. Okay? And what happened in that first group of functions? Did it have a horizontal asymptote or an oblique asymptote? oblique. So basically, if the numerator has a bigger degree than the denominator, there is no horizontal asymptote. Okay? Which means to go find the oblique asymptote. How to find that, we'll take that on next week, okay? Learning how the horizontal asymptotes is enough for one day, all right? The second case was where they all ended up at different numerical values. So they did have horizontal asymptotes, but in all different places. And that was when the degree of the numerator was matching the degree of the denominator, okay? What did we use to figure out where the horizontal asymptote was going to be? So in that section where they came up with different numbers, one of them was at 2, one was at 0.2. How did we determine that? By the coefficients, right? So you're going to take the coefficient of the top divided by the coefficient of the bottom, okay? And it's going to be y equals whatever number that is, because a horizontal asymptote is a horizontal line, and horizontal lines have the equation y equals a number. So this will always come up to be some number. I can't tell you what number because it totally depends on those coefficients, okay? Yes? Yeah, top over bottom, same thing, but just take the coefficients. So like looking back at this, so here, x to the first power was the highest one, so 12 over 6 tells me I should use 2, that kind of idea. So if you want to note that a different way, you definitely can, okay, however you want. So the third case was where everything ended up at 0, okay? So in the third case, there's no mystery as to where your horizontal asymptote ends up. I can tell you exactly what number it's going to be. It's going to be at y equals 0, okay, which is right along the x-axis. That happened when the numerator's degree was less than the denominator, okay? The denominator had a greater power than the numerator. So you guys saw yesterday, it was quick and easy to determine vertical asymptotes, x-intercepts, and holes. And then approaching the horizontal asymptote takes this like process of thinking. First, I have to know the three cases and when they're going to happen. So that's something I have to memorize or learn. Then I have to look at the function and say, okay, is it this one, is it this one, is it this one? If it's this one, least amount of work, right? It's at 0. Done. If it's the second case, second least amount of work. Just take the two lead coefficients, divide them, and you'll know where it's at. Third case, it doesn't have a horizontal asymptote, and you have to do a whole nother group of work to figure out its oblique asymptote, okay? Which is going to be a little bit different, all right? Any questions about this? No? Okay. So do you guys all feel like if you put a function up here, you could determine if it has vertical asymptotes, okay? So let's go back to the function we talked about before.